Our textbook for this class is Thomas's Calculus. I like it well enough. I would hardly use it if I hated it. But every once in a while, it makes what I would call a bad decision. And one of those decisions is where it chooses to cover exponential functions. If we followed the textbook, we would not learn how to differentiate exponential functions until, I believe, chapter 7. And for those of you who are going to go on to take Calculus 2, that would be fine, but many of you aren't. There are majors that only require Calculus 1. And it's simply not acceptable to have students learn differential calculus and still not know how to take the derivative of an exponential function. So we are moving out of order to prevent that from occurring. We'll start by defining a special number e. And the way we define e does not make it obviously seem important. We define e to be the unique constant such that the limit as h approaches 0 of that constant to the power of h minus 1 all divided by h equals 1. It turns out that if you have any number here, this limit exists, and what the limit is, of course, depends on the number you have here. So we define e in this way. There is a number such that if we put it here, this limit is 1, and e is that number. As I say, when you see this limit, your first reaction is probably not, aha, what a natural way of defining a constant. Nevertheless, e is important. It is going to be the key for taking the derivatives of exponential functions. Let's try to take the derivative of an exponential function e to the power of x. Lacking any better idea, we will, for the first time in a while now, return to the definition of the derivative. This is the limit as h approaches 0 of a to the power of x plus h, f of x plus h, minus a to the power of x, all divided by h. And a to the power of x plus h, if we remember our rules for working with powers, that's the same as a to the power of x times a to the power of h minus a to the power of x divided by h. And now you can maybe guess the next step. We've got 2a to the power of x's. It's not clear where we're going with this, but it's hard to see what else we'd do. We'll pull out that a to the power of x. And for our purposes, a to the power of x is a constant. And that surely might not seem intuitive. What do I mean by saying it's a constant when we've got this variable x up here? But as h approaches 0, this x isn't changing. As h approaches 0, this changes, and this changes. This remains constant. It's just a to the x, no matter what h is doing. And we can pull that constant out in front of a limit. That is one of our limit rules, that we can pull constants out. So the derivative of a to the x is a to the x times something. Problem is, we have no idea what this limit is. Or rather, I should say, most of the time, we don't know what that limit is. In the special case where the exponential function has as its base this number e, well, the derivative of the exponential function, we've already done the work here. It's e to the power of x times the limit as h approaches 0 of e to the power of h minus 1 divided by h. And how did we define e? Now it becomes clear why we defined e this way, because we know what this limit is now? This limit is 1. So e to the power of x has a very special property. The derivative of e to the power of x is e to the power of x. It's its own derivative. What is e, by the way? I mean, I defined it implicitly, but you know, just like you can say pi is 3.14 something, we might wonder what the first few decimals of e are. It's irrational, so it's an infinite, non-repeating decimal. Its first few decimal places are those 2.718, and then as I say, it's irrational. This decimal goes on forever. So we know how to take the derivative of n exponential function. But what if we don't have e to the x? What if we have 2 to the x or 0.74 to the x? We'll see soon enough how to handle such cases.